Okay, hello guys, welcome back. Okay, so this is the second lecture for the one-shot series, right? And this series mainly it's just for boards only. And today we will cover the topic of electrostatic potential. So the lecture before this, we mainly covered the first chapter, electric field and Coulomb's law, that part. And in the last lecture, we actually could not cover flux and Gauss law, right? So we will cover that today, and we will also cover the potential part of the second chapter. Okay, so let's begin. So we can begin now. So lecture duration will be around 3 hours. Okay, duration will be around 3 hours. Okay, so this should end about 9:30ish, right? Okay, and the level will be boards level itself. Okay, the level of this series of course is around boards level. Okay, it's primarily for studying the subject until boards level. So we won't be taking any JEE level questions here. Okay, all right, so let's begin. Just give me 1 second, guys. Just give me 1 second. Okay, so we will start with the idea of electric flux. Okay, so we'll begin with that. So for understanding electric flux, first we will take the example of an electric field line pattern. So let's say we have some electric field lines that are horizontal like this, and it's a constant electric field. Okay, so electric flux, if you guys have studied it before, you may already know it has to do with the number of field lines crossing an area, right? So we will choose an area of cross section here. We will choose an area. Okay, some area like this. And if I ask you how many number of field lines, so of these electric field lines, if I ask you to count the number of field lines cutting this area, so let's say this area is a very small area, dA. Okay, so on this area dA, as you can see, some field lines are piercing through it, and from the diagram we can see that the number of field lines crossing it is 3. Okay, number of field lines crossing the area is 3. So electric flux is also similar. It's not the exact count of the number of field lines, but it's a quantity which gives us an idea of how many field lines pass through a surface. Okay, and electric flux mainly depends on 3 things. First is how do you orient this area, which means are you keeping the area like this, parallel to a field line, or are you keeping the area perpendicular to a field line? Okay, this is something that flux depends on, because if you notice something, if you keep the area flat such that it is parallel to an electric field line, then as you can see, number of field lines crossing this area will be 0. Okay, for all areas we will define something known as the area vector. So let's also write that down. So area vector, so whenever you have a two-dimensional area, 2D area, then the area vector is perpendicular to the plane of this area. So area vector will be in this direction such that it is perpendicular to this circular base or whatever the shape is. And this you can also call it as the normal, because it is normal to the area. And this is the direction of the area vector. Okay, this is the direction of the area vector. So if I keep the area like this, such that the area vector, this is the area vector, and it is perpendicular to the electric field vector, right? For this particular area that you are seeing, the area vector is upwards, whereas the electric field is to the right. Electric field are these blue lines. So in this guy's case, no field lines cut through A, cut through dA, right? Because this area is parallel to the field line. So if this is the area, the field line graces through the area, right? It does not cut the area. So through this area, through this part of the area, there won't be any field lines cutting through that area. This means the flux through that area is 0. Okay, this means the flux, we use the symbol phi for the flux, and because this is a small area dA, we use the symbol d phi. So the flux through this area will be 0, the electric flux. Now, so if you place such that dA vector and E vector are perpendicular, in this case we notice that the area vector is perpendicular to the electric field vector, right? What happens is the flux turns out to be 0. The electric flux through the small area turns out to be 0. And as we discussed, electric flux is a measure of the number of field lines crossing the surface. So you can just use logic and understand that if you place this area perpendicularly to the field lines, this is when maximum number of field lines can cut through this area, right? So in this case, let's say I choose the area vector will be in this direction, right? This white vector is the area vector. So in this case, when area vector and electric field are parallel to each other, in this case, maximum number of field lines cross dA, cross the area dA, right? In this case, it is 0, and in this case, it is maximum. So, and what is the speciality of this case? In this case, the area vector is parallel to the electric field. So, the flux or the number of field lines crossing the area, it clearly depends on the orientation. Orientation means how are you placing this area in the electric field. If the area vector and electric field are parallel, then flux is maximum. If the area vector and electric field are perpendicular, then flux is minimum. So it clearly depends on, so flux depends on the orientation. That's the first thing. Depends on orientation. Okay, or this in simple words, you can also say the angle theta between electric field and area, electric field and dA vector. Okay, so this is something that flux depends on, that we can just see. Then the next thing that the flux depends on is the size of the area, how big the area is. Okay, area. The next thing it depends on is the size of the area. This is kind of easy to understand, because if you take a very small area over here, let's say, then only one field line passes, right? But if you choose a bigger area, then more field line passes through it. So this is kind of easy to understand. Bigger the area, more the field lines pass through the area, right? So hence more the flux. So basically bigger the area, more the flux passing through the area. Then the third and the final thing is how strong the electric field is, okay? So you can also say electric field magnitude. This is the third thing it depends on. And to understand this, we can use a fact we learned in the last class. In the last class, we studied that the stronger, the greater the density of field lines. So 1, 2, 3, let's say I am drawing 4 field lines. And this is a 10 centimeter square area, okay? So 4 field lines are cutting through this area, okay? And let's say this is some electric field E. Now let's say I want to draw the field line pattern of field E by 2. Then I will draw only 2 field lines, okay? Now if I place an area of 10 centimeters square, only 2 lines pass through it. So here if the flux, if I say it is phi, here it will become halved, phi by 2. Okay, why did I only draw 2 lines? Because that is a rule, right? When we are drawing electric field lines, the number of lines you draw is proportional to the electric field magnitude. So if it is E here and if I am drawing 4 lines for E, then for E by 2 field, I will draw only 2 lines. So flux is also proportional to the electric field strength. How strong is the electric field? The stronger the field, more the field density and more field lines cross the area. Okay, so these 3 things we can observe pretty easily. It depends on the electric field, how strong it is, how big the area is, and the orientation of the area. Okay, so if we club these 3 things together, then the mathematical relation for the flux is, if I have a small, this is a small area, but I am just drawing a bigger diagram. If it's a small area dA, and the electric field is E vector, okay, at the area dA. Area vector is always perpendicular to the area. So I am drawing it like this. Area vector is this yellow vector. It is always, so if this is the, so it is always perpendicular to the area. And the angle between them is theta. Then the electric flux through dA, then the electric flux through dA area. Because this is a tiny area, it will be a very small flux. So I'll use the symbol d phi. It is given by the dot product of E dot dA. Okay, dot product of the electric field and area. Okay, so here if you open up the dot product, it will be E into dA into cos theta, right? So as you can see, the flux depends on how strong the field is, how big the area is, and this cos theta takes care of the orientation. If the area and electric field are perpendicular, which means the case like this, where area is like this and electric field is like this, okay, electric field is tangential to the area. In such a case where E and E are perpendicular, the flux will be 0, okay. And even in the formula, if you put theta equal to 90 degree, flux will come out to be 0. So this is the formula for the flux through any small area of dA, okay. You cannot write this, so if the thing is, if dA is E dot dA, you cannot always write flux phi by integrating it, and you cannot always write it as E dot A, okay. You cannot always use this formula. So I'll mention when we can use this formula, but If we only have a dA area, which is a very small area, electric field and area makes theta angle between them, then flux is given by EdA cos theta. Now you can use E dot A keeping in mind two things. Okay, first factor is the area must be a plane area if the surface is a how do we write it? If it is a plane surface, okay, if the surface is plane, okay, which means it is not a curved surface. What is the example of a curved surface area? A hemisphere. Okay, so you cannot apply this to a hemisphere, but when it is a plane surface area, which means a triangle, ellipse, circle, something like that, rectangle, then if the area vector, let's say this is the area vector, A vector, and the electric field, this is the first thing, the area has to be a plane area. The second thing is electric field has to be uniform. Electric field is uniform everywhere on surface. Okay, so let's call the surface as surface S, on surface S. So electric field has to be constant everywhere on the surface S. Then you can apply that formula. So let's say electric field is in this direction. This is E vector. And if this angle is theta, then you can say the total flux phi through this large area is E dot A. Okay, only if these two conditions are met, you can use this formula. Okay, so if condition 1 is not met, which means if the surface is, let's say, a curved surface like a hemisphere, okay, then the thing is here you cannot apply this formula. Okay, it can only be applied if you have a plane area, which means a 2D area, okay, a two-dimensional area. All right, so then the thing is, in board exams you can be given the electric field vector in ij cap component. Okay, they will give you let's just take a valued numerical example itself. So if electric field is given as 2 I cap plus 3 j cap plus 5 k cap, okay, the units of electric field is Newton per meter, and the area vector is given to you as 10 centimeter or 10 meter square in the k cap direction. Then all you have to do is take the dot product. Okay, then all you have to do is take their dot product. Area is constant and electric field is also a constant vector, right? Electric field is not changing, it is just a constant vector. So you can find the flux out as E dot A. You can find the flux as E dot A. So how do you take the dot product? So here area, in area we only have k cap. So just multiply the k cap components. So 5 into 10 will be 50. Okay, Newton per meter into meter square. So Newton meter is a unit. Okay, and flux is a scalar. It is the dot product of E and A. So it will be only having a number. Okay, so that is the basic story of the electric flux. If we have a 2D surface and a constant electric field, and usually this is what is asked in boards. Okay, so this is basically the diagram of what we discussed. If we have any surface S and electric field is parallel to the area vector, if electric field is parallel to the area vector everywhere, then you can apply this formula E into S into cos theta. So in this case, this is the plane of this area S. Okay, this is the plane of this area S, and the field lines are cutting the surface like this. Okay, so this is the electric field line, and as you can see, it is perpendicular to the surface S. Area vector is also perpendicular to the surface S. So what is the angle between electric field and area vector? 0 degree. So that's why we have E into S into cos 0. So, or in this case, flux is ES. Okay, so this is the case where flux through the surface S is maximum. Okay, then we have this case. So this case is different. Here the thing is, you can imagine this as a table surface, and on the table we keep this red rectangle, and these electric fields are also parallel to the table surface itself. So in this case, no lines cut the cross section S. The lines are tangential to S. Okay. So the area vector of S is perpendicular to the page. So I am just saying area vector is out of the page. Okay. Out of the page, we represent it as a circle and a dot at the center. This means out of the page. Okay. This symbol implies out of the page. So area is out of the page, electric field is to the right, which means angle theta is 90 degree, right? Here angle theta will be 90 degree, which means 0 flux, okay? Which means 0 flux. Whenever electric field is parallel to the area, flux is 0. Okay, so that is it. Now we move on to a slightly better example, slightly different example, because in the previous cases we were dealing with a open surface, right? Open surface means basically a closed surface means like a cylinder where there is no opening, right? Both the circular faces and the cylindrical face makes it a closed surface. Another example for a closed surface is a sphere. Okay, if you take a sphere, this will also be a closed surface. So now we will try to calculate electric flux in the case of a closed surface. Okay. in the case of a closed surface. For the open surface, it was simple. For the open surface, the flux phi, d phi was equal to E dot ds, E dot dA. Okay, so if you want the total flux, you will integrate this. Okay, so integration of d phi will give you phi. So flux was simply integration of E dot dA. Okay, this was the case for the open surface. Now, in the case of a closed surface like a cylinder, there are three surfaces here, right? The first surface is the circle on the left, the second surface is the circle on the right, and the third surface is the curved cylindrical area, right? Curved surface area. So there are three surfaces here. Now, whenever we have a closed surface, whenever a closed surface is given, there is something to keep in mind. The flux calculation, it will change by a little bit. Instead of this simple integration, we will write an integral sign with a circle in the middle. Okay. So what does this symbol mean? The only change is that whenever a closed surface is given, when we are calculating the flux, we include a circle in the integration. This means cover the entire surface. Okay, this means cover the entire surface. Okay, which means integration of E dot dA. In the case of a closed surface, it would mean that you have to cover the curved surface area, the cylindrical part, these two circles as well. You have to calculate the flux through all the three surfaces. That is what this means. Okay. You have to cover the entire surface. So let's do it. So if I call this circular surface as S1, this other circle as S2, and the curved surface of the cylinder as S3, we will find the flux through S1, S2 and S3. So flux through the cylinder would be flux through surface S1 plus flux through surface S2 plus flux through surface S3. Okay. This is how we calculate the flux when we have a closed surface like a cylinder. Flux through surface S1 is easy because this yellow line is the electric field. That is going to be E. That is going to be E itself. And E is in the rightward direction. There is one more rule, okay? There is one more thing. When a closed surface or for a closed surface, outward normal is taken as the direction for area vector. Okay. So basically what that means is, let's take the example of a cylinder itself. So in the cylinder, it is a closed surface. So at this left circle, if I want to find the direction of the area vector, will it be to the left or will it be to the right? Because there are two perpendiculars, right? There are two perpendicular directions. And the answer is, when we have a closed surface, we always take the outward facing normal as the area vector. Okay. For the other guy, the area vector will be in this direction. Okay. If I take a tiny patch of the cylinder on top of this cylinder, once again area will have two directions, but we will choose the outward direction as the positive area. Okay. So for a closed surface, always we choose the outward direction normal as the positive direction for the area vector. So when we are calculating the flux on the S1 surface, area vector will be to the left and electric field will be to the right. So flux through S1 S1, it will be E into what is the area of the, just a second, what is the area of this left circle? Let's just say it is equal to A. Okay, area of the circles, this circle's area, I am choosing it as A. It will be pi r square, but I am choosing it as A. So E into A, and what is the angle between E and A? 180 degree. So into cos 180. This is the flux through S1. Now, what about the flux through S2? It will be E into A, right? Because here the area outward normal is in the right direction. So here area vector is outwards and electric field is also outwards. So it will be E into A. Or basically E into A into cos 0, right? And now we also need to calculate it for the curved surface of the cylinder. How do we do this? So for this, you need to notice something. The electric field is always tangential to the cylindrical surface everywhere, right? Electric field, as you can see, it is tangential to the cylindrical surface. Area vector is normal to the cylindrical surface. So the angle between them is 90 degree, right? And whenever E and dA have a 90 degree between them, the flux is 0. So it will be E into dA into cos 90. Okay, so this will be just 0 for all the terms. So for the curved surface area, the flux will be 0. So EA cos 180 is minus EA and EA cos 0 is plus EA, and this will come out to be 0. So the net flux through the cylinder is 0. There is another way to visualize this. So as I said earlier, flux, you can imagine it like a count for the number of field lines, right? So if you notice how many field lines cut through the cylinder, if you try to count it, it will be what? 1, 2, 3, right? So here we have 3 field lines entering the cylinder, and these 3 field lines, they continue along the cylinder and exit at the other end, right? So here we have field lines entering and here we have field lines exiting. So any line that enters also leaves the cylinder. So for a closed, where was that page where yep. So for a closed cylinder, for a closed surface, you can keep it like a rule. Field lines entering contribute negative flux and field lines leaving the surface contribute positive flux. Okay, this is easy to understand. If you notice, the electric field lines here, they are entering, right? They are entering the cylinder, but normal is to the left, electric field is to the right, angle between them is 180. Cos 180 is negative, right? So the flux will be negative here. So entering field lines contribute negative flux and exiting field lines contribute positive flux. So from here we have a negative flux of minus EA, and from here we have a positive flux of plus EA, and in total they are 0. So basically whenever we have any body, okay, like you can take a cone for example, and through this cone we have some electric field line cutting like this, okay, and if I ask you what is the total flux, what is the total flux through the cone, you don't have to do any calculations. Any field line that enters the cone also leaves the cone, right? Any field line which enters the cone also leaves the cone. Entering field line contribute a negative flux, exiting field line contribute a positive flux. So in total it will be simply 0 itself. In total it will be simply 0 itself. So if we have some surface which we keep in an external field like this, okay, and if we can see that any field line entering is equal to, it also leaves the surface, then the total flux will be 0. You can also take the example of a sphere, okay, and let's say it is kept in a field like this. Here also any field line that enters also leaves, right? Any guy who enters also leaves. So in this case the net flux will be 0, okay. So this is something to keep in mind. And now we can calculate, we can move towards Gauss law, okay. So now we are going to calculate the flux through a spherical surface when we have a charge q at the center of the sphere, okay. So for the charge q we discuss the electric field line pattern, right? For the charge q we discuss the electric field line pattern. It is radially outward, which means all these lines basically connect them to the center of this q charge. That is how the pattern will look like. All these field lines originate from the center like this, okay. It's going to be uniform. The diagram may not look like that, but the direction is everywhere radially outward. If you need the field here, okay, connect this point to the center and it will be radially outward like this, okay. And if you need the field here, connect it to the center and it will be radially outward like this. So the field direction is always radially outward. So if I choose a sphere here and I want to calculate this flux through this sphere. We are trying to calculate the flux through this sphere. So first we will write it down. It is equal to the integration of E dot dA, right? It is equal to the integration of E dot dA. And here the thing is, there is a nice thing. We have a plus Q charge here, and the distance of this point from the plus Q charge is also equal to R. The distance of this point from the plus Q charge is also R. So on this sphere, anywhere you choose a point, the distance from the plus Q charge will be R. Now, because the distance from the plus Q charge is constant, we can say the electric field has a constant magnitude. Okay. Electric field here, electric field magnitude is constant everywhere on the sphere. Okay, this is because all the points on the sphere, they are at a distance r from the point r from the plus Q charge. So by symmetry, we can say that all the points will have the same magnitude of the field. Okay, so now the next thing is we choose a tiny patch of ds area somewhere on the sphere. This is a very, very small patch. Okay, so imagine a very tiny rectangular patch or something on the surface. So at this location, electric field is of course radially outward, right? Electric field is radially outward, and the area vector is perpendicular to the sphere, perpendicular to the sphere's surface. And this is, you can say, a property of a sphere itself. At any point, if you want the normal vector, it is along the radius. Okay, the same property is also applicable to circles, right? The normal vector is along the radius itself, along the radial direction. Same is here also. So here the normal vector, which is also the area vector's direction, is in the radially outward direction. Electric field is also radially outward. Electric field is also radially outward, which means the angle between E and ds is 0. They are parallel. Similarly, you can choose a point here also. Here also, if you choose a point, a small area, the area vector will be radially outward. Electric field will be radially outward as well. So here also the angle theta is 0. So what we can do here is, this flux term, we can simplify it. So open up the dot product. So it will be E into dA into cos theta. But theta is 0, right? Theta is 0 everywhere. So you can write it as cos 0. Now the thing is, cos 0 is of course 1. But we also notice that the electric field is a constant everywhere on the sphere, right? We are performing this integration on the sphere. Performing on the sphere. We are performing this integration on the sphere. So electric field is constant everywhere on this sphere of radius r. So we can also take it outside. So what is left inside is integration of dA. And this is actually easy to calculate. Integration of dA means add up dA areas on the surface of the sphere. Okay. So on the surface of the sphere, you have to add up the areas. So if you add up the total area of the sphere, what do you get? 4 pi r square. So this will be E into 4 pi r square. Okay, this is the flux through the sphere of radius r. Okay, if the electric field at that point is E. Now we also know this formula for E, right? We discussed this earlier. E was actually KQ divided by R square. We also discussed this magnitude in the last lecture. So if I substitute that here, I get, instead of K, I'm going to write 1 by 4 pi epsilon naught Q divided by R square multiplied with 4 pi R square. So you can cancel out the 4 pi R square, right? And the beautiful thing here is that the total flux is coming out to be Q by epsilon naught, and it has nothing to do with the radius. Okay. The total flux through the sphere has nothing to do with the radius. This you can also visualize pretty easily. If I just draw 4 field lines coming from the center, okay, 4 field lines I am drawing, then it doesn't matter if you choose a smaller sphere, or a larger sphere. Okay, it doesn't matter. The total number of field lines cutting it is still 4, right? The total number of field lines cutting the inner sphere and the outer sphere are both 4, right? So if the inner sphere has a flux phi through it, then the outer sphere will also have the same flux. So flux will have nothing to do with the radius. So if this radius is R1 and this radius is R2, flux will have nothing to do with this radius. Okay, and that is what we are seeing here also. The flux only depends on this charge Q, right? Flux only depends on this charge Q at the center. So this is something to keep in mind. Actually, it does not even have to be a sphere. You can keep this plus Q charge at the center. This is also actually the statement of Gauss law. You can choose any arbitrary shaped closed surface. Okay, this has to be a closed surface. There should not be any openings on the surface, and Q is enclosed inside, and Q is inside. I'm calling this surface as S. So Q is inside S. In this case also, if I ask you what is the flux through S, you don't have to do any separate calculations. I know the result for a sphere, right? For a sphere, we discussed this. So for a sphere, the flux through the sphere was Q by epsilon naught. And if 1, 2, 3, 4, 5, 6, if 6 lines are cutting the sphere, then the same 6 lines will also cut S. So here also the flux will be the same. The flux will be the same, Q by epsilon naught. Okay, this is also actually the definition or the statement of Gauss law. Okay, we'll discuss Gauss law in a bit. But yeah, it does not matter what the shape of the surface is. The only thing that matters is how much charge is inside the surface S. Okay, so as you can see in this particular diagram, we calculated this using the results we know. We proved that the flux is Q by epsilon naught. But even if you choose any arbitrary shaped surface, it has to be a closed surface. Then also the flux is the same. Okay, the shape does not matter. If n number of field lines are leaving plus Q, which means n lines will cut the sphere, then the same n lines will also cut this random surface. Okay, so hence the flux will be the same here and there. So now this is what Gauss law is. Okay, but Gauss law, its left hand side is the flux through any closed surface. Flux through any closed surface. This mathematically we can also write it as integration with this circle E dot dA. Okay, these two things mean the same thing. This is actually equal to the net charge enclosed within the Gaussian or within this closed surface divided by epsilon naught. Okay, so basically if you have any closed surface, the total flux through that surface is given by the charge enclosed, the magnitude of the charge enclosed within that surface divided by epsilon naught. Okay, so that is it. That is your Gauss law basically. If you have any closed surface, flux through the surface is q by epsilon naught. Here also q by epsilon naught, there also q by epsilon naught. Okay, and that is Gauss law. Now we will of course use it in some situations. Then yeah, so there are some pointers here. Flux through any okay, so Gaussian surface. Gaussian surface is just another name for the closed surface. Okay, so basically any closed surface that you can draw, that you can treat it like the imaginary Gaussian surface. Okay, Gaussian surface. It just has to be, it has to be a closed surface. There should not be any openings. So the flux through the Gaussian surface is independent of the shape. This we saw earlier. In the sphere case or any other shape, you can also keep a cube or any three-dimensional surface. It can be. So here also if you keep plus q at the center, the total flux through the cube, will be q by epsilon naught itself. Okay. We should also draw the lines, the field lines to imagine flux. So there will be these field lines cutting the surface, and hence as a result there will be flux through the cube, and the total flux will be definitely q by epsilon naught according to Gauss law. Okay, even though we are not going to calculate the left side of the Gauss law here, E dot dA, because that will be very complicated for this surface or for this surface. Flux through Gaussian surface depends only on the total charge present inside the Gaussian surface, right? So which is basically the right hand side of Gauss law. Okay, Q enclosed, once again I'll just clear that. So if this is our Gaussian surface and inside we have a plus Q1 charge and a minus Q2 charge which is negative, and a plus Q3 charge as well, then Q enclosed will be, okay, first observe the boundary of the surface, and Q enclosed will be sum of the algebraic sum of the net charge inside. So Q1 is positive, Q2 is negative, Q3 is positive, that's it. Okay, this is going to be Q enclosed. It doesn't matter if there is a Q4 outside, you will not include it here. This is the Q enclosed, which means charge enclosed inside surface S. Okay, so that is the only thing the flux depends on. That is point number 2. It is independent of the position of charges inside the Gaussian surface. That is also straightforward, because if you take this Q1 and put it in place of Q2 and minus Q2 you put it here, then also Q enclosed is the same. So it doesn't matter where exactly these charges are placed, Gauss law is still true itself. Okay. Then electric field intensity at the Gaussian surface is due to all the charges present inside as well as outside the Gaussian surface. So basically if we are talking about the electric field here, E vector, this E vector is the field due to all the charges. Okay, so this can be asked in your board exams or mains. Okay, all charges present inside and outside, yes. So basically in the Gauss law, the left hand side E dot dA, here the electric field is due to all the charges present inside and outside S. So if you're applying Gauss law in this surface S, then the field, let's say you're choosing a patch on the surface S, let's say I'm choosing this patch, and here the area vector is like this, dA vector, and the electric field vector is like this. Okay, we don't know how it will be, but in some random direction. Then this electric field which you will use to calculate the flux will be due to all the charges inside and outside. So my Q1 minus Q2, Q3, Q4, all of them together will contribute this E. So this E is due to Q1, the minus Q2 charge, the Q3 charge, and the Q4 charge outside. Okay, the total field due to all these charges is going to be your E. Whereas this thing on the right is only charge inside. Okay, so this term is charge inside. Total charge inside S. Okay, so that is it. That is all the points. Now, so now we have a question. You guys can try this out. Try this question out. Yes, so what answer are you guys getting for this question? You can just answer in terms of epsilon naught. Okay, you don't have to substitute epsilon naught. So here, what is the, if I want the net flux through this Gaussian surface, even though the shape of the surface is very weird, we don't care about the shape. We only care about the charges present inside. So just add them up. 2 plus 4 is 6, 6 minus 3 is 3. So in the numerator, we have 3 microcoulomb. This is the Q enclosed divided by epsilon naught. Okay. So basically, if you want the final answer, you can just substitute everything in SI. So 3 into 10 raised to minus 6 coulombs divided by epsilon naught, substitute it as 8.85 into 10 raised to minus 12, and you will get the answer in SI units. Okay. So for calculating the flux through any Gaussian surface, just calculate the total amount of charge inside the Gaussian surface. Okay. Then we can use Gauss law to, so these 3 derivations are also important for boards. Okay. So basically in the NCERT, you just have 3 examples. First is the electric field due to a sphere, uniformly charged sphere. Then you have a cylinder, and finally, not a cylinder, a line charge, okay, an infinite line charge. And then finally, an infinite sheet. These 3 examples are given. Okay, so these 3 derivations will be important for boards. So for sphere, the primary thing to keep in mind is that the electric field line pattern will be similar to that of a point charge. Okay, so here we are talking about a uniformly charged sphere, and the charge is lying on the surface area. Okay, so let's say we want the field at some point which is at a distance small r. Radius of the sphere is capital R, and the point where we need the electric field is at a small r distance, okay, is at a small r distance. So we will use Gauss law to find that electric field, okay. So because the field pattern is similar to the point charge example, the same previous one, the left hand side of Gauss law, that electric flux term, it will be the same as the previous one, which is going to be E into 4 pi r square, E into area of the Gaussian surface. This will be the left hand side of Gauss law. Right hand side is count the amount of charge inside this blue surface. So the amount of charge inside this blue surface is small q, right? The total charge on this sphere is small q. So q enclosed will be q. Divide it with epsilon naught, and that is it. You get the electric field. It will be 1 by 4 pi epsilon naught q by r square. So for boards, you will have to write some extra steps, okay? Or which is basically kq by r square, the same result as a point charge. So if you have a uniformly charged sphere, charge is uniformly spread on the surface of the sphere. The center is at point O. Then if you want the field at some point outside, okay, then the result is the same as that of a point charge, which is kq by r square. Okay, result is the same as that of a point charge. So you can also think of it like you can replace this sphere with a point charge at the center. And that way also you can imagine it. And then the thing is, there you can also find out the electric field inside. Okay, for that you just take a spherical Gaussian surface inside the sphere, and let's say this radius is also some small r. So for inside points, this is the sphere, this is my Gaussian surface of radius small r. So here also let's just assume there is a field in the radially outward direction. Okay, let's just assume there is a field here, and I'm going to call it E. So the left hand side of Gauss law will be E into surface area of the Gaussian surface, right? 4 pi r square. But the right hand side is going to be Q enclosed. Q enclosed will be 0 because all the charge is at the surface, right? So here Q enclosed will be 0. So which means the electric field inside is just 0 everywhere. So for a uniformly charged sphere, the field inside will be 0 and the field outside is the same as a point charge. Okay. So for small r less than capital R, which means inside the sphere, the electric field is 0. And for outside points, it's the same as a point charge, which is kq by r square. Okay. So this is the situation with a uniformly charged spherical shell. Okay. Then we have the second derivation, which is the infinitely long line charge. So for the infinitely long line charge, remember the field line pattern. So imagine this as the z axis. So the field lines will be perpendicular to the z axis. Okay, something like this. or in other words, it will be along this circle that you are seeing. Okay, along this circle, parallel to the circle basically, and perpendicular to the infinite line. Okay, so what is this charge? Basically, we have a line charge, which means everywhere on this line we have charge distributed. Okay, we have charge distributed on this straight line everywhere. And for this line charge, the charge per unit length is given. Okay, it's a constant. Charge per unit length is given. Okay, so basically if you choose 1 meter length, the charge will be lambda. So here the thing is, the field pattern is, it's basically, if you draw the top view of the diagram, you will see a circle, right? And this is where the line is coming out of the page, and the field lines will look like this basically. The top view picture is slightly more clear. Okay, it will cut the cylinder's curved surface area perpendicularly. These field lines will cut the cylinder's curved surface area perpendicularly. This is the electric field line pattern due to an infinitely long line charge. Okay, so here how do we calculate the flux? Here it's actually easy. We have three surfaces, right? We have three surfaces for the cylinder. So we just discussed this a while back. We calculate the flux through all the surface. So through surface S1, it's very easy. The field lines are tangential to the surface, right? The field lines are tangential to the surface, which means area vector and electric field vectors are perpendicular to each other. So theta is 90 degree. So here what will be the flux? Flux through surface S1 is the same as the flux through surface S2, and they are both equal to 0. Okay, because simply electric field is tangential to the surface. Flux will only be through the curved surface area of the cylinder. Okay, let's say you choose a tiny patch on the curved surface area of the cylinder. Okay, and the side view, it is over here. So here, as you can see, the area vector and the electric field vector, they are parallel to each other. Here also the area vector and the electric field vector, they are parallel to each other. So any point on this curved surface of the cylinder, CSA of the cylinder, the electric field and area is parallel, theta is 0. So only the curved surface will have any flux. So flux through the third surface, we will use integration of E dot dA, and this we will simplify as integration of E into dA into cos 0, it is 1. And because all the points on the cylinder are at a r radius from the center, by symmetry we can say their electric field magnitudes are all the same. So because E is constant, we can take it outside, and what is left inside is integration of dA. Now what is integration dA? We are calculating the flux on the curved surface of the cylinder, right? That is what phi S3 is. So this integration dA is actually the curved surface area of the cylinder. This is the curved surface area of the cylinder, which is E into 2 pi RL. So our Gaussian surface is this cylinder of length L and radius small r. So curved surface area will be E into 2 pi RL. So we calculated left hand side of Gauss law. Left hand side of Gauss law is the net flux through the Gaussian surface. So that was phi S1 plus phi S2 plus phi S3. These two were 0. So the only flux is E into 2 pi RL. Now this will be equal to Q enclosed by epsilon naught. Okay. Now Q enclosed, this is a cylinder whose length is L, right? And inside we have a line whose length is L. So on this length L, what will be the charge? Lambda into L. So Q enclosed will be lambda into L divided by epsilon naught. So this turns out to be independent of the length L because it cancels out. And the electric field comes out to be lambda divided by 2 pi epsilon naught R. Lambda divided by 2 pi epsilon naught R, or you can also write it as 2k lambda by R. If you want to express it in terms of K, you can write it as 2k lambda by R. So this is the field due to the cylinder. Okay. Now, so we are done with 2 derivations. So now there's one more. And this is the infinite sheet. Okay. So basically this is you can consider this as a very long rectangular sheet with a uniform positive charge on its area, and it's very long. Okay. So you can consider this as an infinite sheet. Okay. And we are trying to find the field due to this. So here, if I say this plane, right, this plane of the rectangular sheet, if I draw only its plane over here, so basically let's just say this sheet is in the xy plane. So this is the xy plane. Okay. Then here the Gaussian surface we would choose is a cylinder. So from this view, the cylinder will look like this. And you should also remember the field line pattern for this. Okay, because it is an infinitely long sheet. Everywhere on the right, the field will be along the right direction. Okay. Why is it to the right? Because you can just imagine a positive charge here, right? So at this location, the positive charge will repel in this direction. So as you can see, there is an x component to the electric field, right? So everywhere on the right side, the field will be along the right direction, and everywhere on the left side, the field will be along the left direction. Along the left direction. Okay. So this is how the fields look like. Okay, and also by symmetry, if this distance is x and this distance is also x, then there is no difference between the right and the left side. So if the field here is E, then I can say the field here also is E in terms of magnitude. Okay, that is just simple symmetry. Now we can apply Gauss law on this cylinder. Okay, this cylinder is our Gaussian surface. So here the situation is slightly easier because on the curved surface area, electric field is in the right direction, area vector is perpendicular. Right, so flux through the curved surface area will be 0. Flux through this circle, flux through circle 1 plus flux through circle 2, we have to calculate. So in circle 1, as I discussed earlier, we have to take the outward normal as the area vector. Okay, and over here also we have to take the outward normal. Outward normal means away from the cylinder. Away from the cylinder. Okay, not inside. So here the flux will be E into A. Here also the flux will be E into A. So this will be EA plus EA, which is 2EA. This is the left hand side, and the right hand side will be Q enclosed by epsilon naught. So on this white cylinder, charge is enclosed on the circle in the center. Okay, in this view it will be a bit more easier to understand. So basically this common circle, right, the intersection of this cylinder with that sheet, so that will be this circle whose radius is equal to the radius of the cylinder, right? If the radius of the cylinder is r, on this common circle also the radius will be r. Okay, so the area of this part will also be the same area A, area of the cylinder. So what is Q enclosed? So for writing Q enclosed, the charge per unit area, which is denoted using sigma for the sheet will be given. So sigma is used for the symbol, sigma symbol is used for the charge per unit area of the sheet. So if I know the charge per unit area of the sheet, I can write the charge on this circle whose area is A. That will be sigma, which is charge per unit area, into area A. This will be the charge on this circle in the middle. So this is Q enclosed, just divide it with epsilon naught and you will get the answer. So E will be area cancels and the electric field is sigma by 2 epsilon naught. Okay, so if you have an infinite sheet, then on either side of the sheet, so if this is your infinite sheet, then on this side everywhere on the right side everywhere the field is to the right, okay, and the magnitude is sigma by 2 epsilon naught, and on the left side the field is to the left, magnitude is still the same. So this is the field due to an infinite sheet, an infinite two-dimensional sheet. It should also be uniformly charged. Okay, so these three derivations are required for the NCRT. Okay, it's given in the NCRT. So these three can be asked in your board exams. Okay. For the competitive exams, there are some extra derivations as well, but that we don't need to cover here. Okay, so now the electric dipole topic. There were two topics left from the last lecture. So electric dipole in a uniform field. Okay, so firstly we have a constant electric field everywhere. I am taking the field to be along the x direction, and we are placing a dipole in this field. Okay, so let's say this is the plus q charge and this is the minus q charge. So here we are going to analyze something. We are going to see that there will be a torque acting on this dipole, okay, and the net force on this dipole is 0. Okay, so firstly, if the electric field is in the right direction and it is constant, uniform electric field means it's a constant electric field. So on the plus q charge, the force will be to the right, okay, same direction as the field, and magnitude will be charge into electric field, okay, and on the negative charge it will be opposite to the electric field direction. Magnitude will be charge into electric field, okay. So net force, as you can see, it will be 0. On the positive charge it will be along electric field, on negative charge it will be opposite to electric field. So using vectors, if you want to write force on the plus q charge, it will be q into E vector, and force on the minus q charge, it will be minus q E vector. So the net force is basically you add these two up, which is 0. QE and minus QE will be 0. So if you have a dipole, okay, if you have a dipole which is kept in a uniform electric field, which is a constant electric field, then the net force on the dipole will be 0. Okay. If it is a non-uniform electric field, then it may or may not be 0. Okay. For a non-uniform electric field, this means electric field changes from position to position, then the net force will be Q into electric field near the positive charge minus Q into electric field near the negative charge. Okay, it's a non-uniform field, so electric field near the positive is different from the electric field near the negative. So this need not be 0, right? This can be non-zero. But if you throw it into a uniform electric field, then the net force will be 0. So this is the first idea. Next idea is, as you can imagine, this is going to rotate the dipole, right? This is going to rotate the dipole about the center of mass of the dipole in the clockwise sense, right? You can imagine as pulling on these two balls like this, so it will rotate it clockwise. So that torque we are trying to calculate. So there are two ways to calculate it. It's either you can use vectors, or you can use just direct formula, but I am going to use vectors, okay. So what I will do is, so dipole moment vector is in the direction from minus q to plus q, right? So what I'll do is, I'll say from the center of mass to this charge, this vector I am calling it as A vector. Okay, its position vector I am calling it as A vector from the center of mass to the positive charge. Okay, and the direction of A vector is in the direction of the dipole moment vector. And the position vector from the center to the minus q, that will of course be minus A vector, right? If this is A vector, this is just minus A vector. Okay, its direction is opposite to A vector, and the length of and this length is the same as this length, right? So in the previous session we discussed dipole. We said that the length of the dipole was 2a, right? This is what we took the length of the dipole to be. Now if you want to calculate the torque, the basic definition is the torque on any system is simply sigma of r cross f. Okay, so in any system, if there are multiple forces acting, you simply take the summation of this cross product, r cross f. So here we have two forces acting. So there will be two terms for the torque. So first let's write the torque due to this QE acting on the positive charge. So r cross f. So position vector is A vector cross, what is the force vector? Q into E vector. Okay, you have to write everything in terms of vectors. This is the torque due to the force acting on the plus q charge. Now the torque due to this force. So here what is the position vector? Minus a vector cross. What is the force? Minus QE vector. Right? So minus and minus will make this plus. So this is a cross QE, this is also a cross QE. So this will become 2a vector cross QE. Okay, so now we will do some tricks here. So we take the charge Q, this is a scalar, right? So we take it and place it here. And this becomes 2q into a vector cross E vector. Now what is this vector on the left? This is the dipole moment vector. Dipole moment's magnitude was charge of the positive charge into distance between the two charges, which was 2a. So dipole moment's magnitude was 2aq. Okay, and a vector is in the direction of the dipole moment vector itself. So this is nothing but p vector. This is nothing but p vector cross E vector. Okay, and this is the relation that is important to us. The torque acting on a dipole is P cross E. So if you have a dipole in an electric field, in an external electric field, then there will be a torque acting on the dipole, okay, which will rotate the dipole. And this torque is given by the dipole moment cross the electric field, their cross product. Okay, and if you want the magnitude, what is the magnitude of a cross product? PE sine theta. It will be PE sine theta. Okay, so just do P cross E. So basically the torque is into the page. Okay, in this case, the torque direction will be into the page, which means it is trying to rotate the dipole clockwise. So the dipole will try to rotate clockwise. If dipole moment and electric field are parallel to each other, then the torque will be 0, which means it will be in equilibrium. Same is the situation if it is anti-parallel. In this case also, torque will be 0. Okay, and torque is maximum when theta is 90 degree, right? So when the dipole moment and the electric field are perpendicular to each other, this is when torque is maximum. Which is equal to P into E. Okay, this is when the torque is maximum. Okay. Yes, I am looking at the chat. You can ask your questions if you want to. But I'll be focused on the lecture more. Okay. All right. So now we are done with this. So we're done with the torque as well. Okay. So now we can talk about the potential energy part. Okay. So in the first chapter, basically the fields chapter, in the first chapter, we were paying attention to fields and forces, right? Electric fields and electric forces. Now, in this chapter, we will bring in energy into the picture as well. Okay. This was chapter 1. In this chapter, we will start talking about energy also. Electrostatic energy. We call it the potential energy. this is similar to how we went from talking about forces in NLM in 11th standard. We started with forces, and in work power energy we moved on to energy, right? This is also similar. Energy is a useful way to look at physics problems. Okay, so we will move on from fields and forces to the energy in this chapter, mainly potential energy. So first thing is we need to take a look at the two forces, right? The Coulomb's force, which is the electrostatic force of attraction or repulsion, and we saw this in the Coulomb's law part. Then we have Newton's law of gravitation, which is the force of attraction between 2 point masses, right? This was G m1 m2 by r square. Now these two formulas, these two equations have a similarity. In both of them, the dependence on r is identical. It is inversely related to r square, right? So in the first case, if we take two q1, q2 charges, if they are positive charges, let's say, then their repulsion force, this force F, depends on what this distance is, okay? And it depends on 1 by r square. Similarly, if you take two masses, 2 point masses, m1 and m2, which are at the same distance r, here also the thing is the force, the masses will only attract each other, whereas Coulomb's force can be attractive or repulsive. But here also the magnitude is inversely proportional to 1 by r square. So these two relations or these two laws are actually identical because their relation with r is the same. Okay, so then in electrostatics, not electrostatics, in gravitation, we talk about the gravitational field or the gravitational force, and we discuss that the gravitational force was a conservative force, right? Conservative force. Okay, and conservative force, the main definition was related to work done. Okay, this term was used with something related to work done. So basically, if you have a conservative force, the main idea is if you go from a path A to a point B using any path, okay, so you're going from a point A to a point B, and this conservative force is acting on you. Okay, so in this case, let's say the gravitational force mg is acting on you. Okay, then it doesn't matter which path you choose from A to B. You can choose any of the infinite paths connecting A and B. The work done by this conservative force, okay, this will be path independent. This will be path independent, meaning it doesn't matter which path you choose, the work will come out to be the same in all cases. Okay, and this will only depend on, this only depends on the initial position and the final position on A and B. Okay, we can try a simple exercise to remember this fact. So if we have a, let's take a gravity question itself. So when we take a mass, right, that is at a height h1 from the ground, this was the initial position of the mass, let's say, mass is m, and of course the gravitational force is acting on the mass m, and I want to take it to some position over here. which is at location H2. This is at location H2. Okay. So it doesn't matter which path you choose. You can directly go through a straight line. You can go along the x-axis, then go along the y-axis. You can go along a circular path. Whichever path you choose, work done in this first path, work done by mg in the second path, work done by mg in the third path, they will all be the same. Because the initial point A and the final point B are the same. So work done through the first path, work done by mg in the second path, work done by mg in the third path, they are all the same because initial point and final point are the same. And if you remember, this is actually equal to minus delta U. Delta U is change in potential energy. So going from a height h1 to a height h2, the potential energy increased, right? So delta U is actually mg delta h. Okay, if this height difference is delta h. So if you take a mass and increase its height by delta h, the potential energy increases by mg delta h. So this will be equal to minus mg delta h. So the work done by mg in path 1, path 2, path 3 are all equal to minus mg delta h. So the main idea when we discuss conservative forces in work power energy is the work done by the conservative force. So in this case, these are work done by mg. Okay, work done by mg. Mg gravitational force was the conservative force in this example. So one work done by the conservative force from some path A to some path B, sorry, some point A to some point B will be negative delta U. Okay, this minus sign is also important. So work done from A to B will be negative delta U means negative U final minus U initial, which is U initial minus U final. This is the thing that we will need in this chapter now. Work done by the conservative force to go from A to B is equal to UA minus UB. So this is something that we are going to be using in this chapter. Okay, so this is how we relate the work done by the conservative force to the potential energy. In fact, this is how the potential energy term is derived itself. Okay, potential energy is only valid for conservative forces. Okay, so if you take any non-conservative force, you cannot derive a potential energy for that. Potential energy you can only talk about for conservative forces. Okay. If potential energy depends on the choice of reference level, why doesn't changing the zero level change the motion of the object or the work done by the gravity? Yeah, because if you choose the reference, so typically in the normal gravity problems, we choose the ground as the zero potential energy level, right? And then we write everything relative to that. So if we have a point which is at a height h above the ground, then we say that the potential here is mg h. But you don't have to do that, right? You can also say that the ground is at a different potential. You can say the ground is at some u naught potential energy. then the thing is everything will increase by u naught. Okay, if you are saying ground is u naught, here it won't be mg, but it will be mg plus u naught. Okay, now let's say you drop the ball. So if you choose ground to be 0, then the potential energy here is mgh, right? If you go a height h above, potential increases by mgh. Okay, so 0 plus mgh, here it will be u naught plus mgh. Now let's say we release this ball, so it falls under gravity. It falls under gravity, and let's say we are interested in finding the speed before it hits the ground. Okay, so now you can use energy conservation. Here potential energy is mgh, kinetic energy is 0. And here potential energy is 0, kinetic energy is half mv square. And you will get the standard result, V is equal to root of 2gh. And here also you will get the same answer, because now final potential energy is u naught, initial potential energy is mgh plus u naught. So the u naught cancels on both sides. Okay, that is because motion, mainly the only thing that is important is delta u. Delta u is the important, you could say, parameter. Okay, not potential at any point. So so yeah, I hope that clears it. It doesn't matter what you choose as the reference, the change in potential will always be the same. So if this is 0.1 and this is 0.2, u1 minus u2 will be mgh here and here also. Okay, so where were we? Yes, work done from A to B. So that is done. So this is something that you should keep in mind, guys. This is in fact how potential difference is defined for any conservative force. So this W is work by a conservative force. Okay, and conservative forces for our syllabus, the first thing we covered was gravitational. Okay, and then we also discussed the spring force. Okay, we discussed the potential energy for the spring mass system. And now we are going to cover the third conservative force, which is electrostatic force, which is static force. This is the third one. Okay, and we don't have to, and the reason why this is a conservative force is because it's exactly similar to gravity, right? There is no difference between the main law. They're both inverse square laws. Everything else are constants, but force is inversely related to r square in both these laws. So now we can define a potential energy for the electrostatic force. So that is what we are going to do now. Kirtan, frictional force. That is because for friction, the work done will be path dependent. Okay, that's a good question. So we go back to the basics from point A to point B. Let's say this is on a horizontal table surface. Okay, so this distance is d1 and this distance is d2. So here the thing is, if you assume a friction force, let's say you are dragging some object along this d1 line, then of course at any point in the middle, the friction force will oppose the motion, right? Let's say the friction force is F and displacement is in this direction, right? Displacement is in this direction. So you are slowly dragging this particle from A to B. Friction force is opposite, displacement is along this line. Okay, so if you say in this path the work done is W1, W1 will be minus F into D1. It depends on this D1, force into displacement, right? Force and displacement are opposite to each other everywhere, so it will be F into D1. Negative sign because force and displacement are opposite. But when we talk about this curved path, okay, and its distance is d2, here let's say at some intermediate point, the particle is over here. Here if you're trying to move it in this direction, let's call it ds displacement. Here the friction force will be exactly behind. Okay, friction force will be exactly opposite to the displacement. Here if you try to calculate the work done and call it as W2, the W2 will be different. It depends on this distance, which is minus F into D2. So here you are dragging the body along a longer path, so work by friction will be different. It will be F into D2, and here if you are dragging the object along this line, it will be F into D1. So as you can see, work is different, right? Going from A to B along two paths means work is different. But that cannot be the case. Okay, for a conservative force, if you choose any path connecting A to B, the work should be the same. The work should be the same. All right. So now we can discuss this. Okay, so now we are going to discuss, okay, so this formula we discussed, okay, delta U always means U final minus U initial, and this is equal to negative work done by conservative force, or you can remember it like this: work done by conservative force from A to B is equal to UA minus UB. Okay, we are going to use this, after that it will be clear. So we can remember it like this. Okay, so now we are going to derive an expression for change in potential energy. Okay, so potential energy, it mainly depends on the orientation. So here initially Q1 and Q2 was separated by a distance Ra. So at this location there was some potential energy, and then we moved it to a different location Rb. Okay, we are keeping Q1 over here itself and we are moving around Q2. So because the position changed, there will be a change in potential energy as well. Okay, so we are trying to calculate that delta U in this case. Okay, we are moving Q2 from here to here. Okay, so in class 11th, the work topic, how was work done calculated if we simply look at straight line displacement. Okay, at this point, let's say P, if we displace an object by a tiny displacement of dx, and the force is also in this direction itself, then the small work done in this tiny step is F into dx. Generally it is F dot S, but here force and displacement are parallel. Then if I want the work done by this force F from P to Q, then I will just integrate this. Okay, integrate F dot displacement will give you the work done, right? So here we are trying to calculate the work done by the electrostatic force. So of course, if you place Q1 and Q2, the Q2 will be repelled away by the electrostatic force. So this electrostatic force is the conservative force, and that will perform some work on the Q2 charge. So we are trying to calculate that. So this is, let's say, the initial line, and here we have Q1 fixed at this location, and at some intermediate time at a distance r we have the other charge Q2. Okay, so on this Q2 charge we have the Coulomb force acting to the right. We're assuming both of them are positive charges. What is the magnitude? Magnitude is k Q1 Q2 by r square. Okay, this is a variable force, that is why we need integration. Force changes with this distance r. Now let's say we move it a tiny step forward. So this is R, so this tiny step we can call it as dr. So in this tiny step, the small work done will be F into dr, which is K Q1 Q2 into dr divided by r square. So now let's integrate this. So we need to calculate the work from RA. So this initial location was RA till RB. So initially it was RA away distance, RA away from Q1, and now finally it is RB. So initial R value is RA and we are moving it till RB. Integral dW will give us the total work done from A to B, right? This will give us the total work done going from A to B by the electrostatic force. So what does this integral become? Integral of dr divided by r square is actually minus 1 by r. Okay, it's actually minus 1 by r. So we will put the limits as well. Upper limit is RB and lower limit is RA. So this thing will become KQ1 Q2 into 1 by RA minus 1 by RB, I guess. 1 by RA minus 1 by RB. This will be the work done in going from A to B by the electrostatic force. Now, once again, work done in going from A to B is KQ1 Q2 into 1 by RA minus 1 by RB. Okay, so what did we do so far? We calculated the work by this electrostatic force in moving Q2 from here to here, from A to B. Okay, and then came out to be this value. So now we know how to relate this to the potential energy. Okay, this we can write it as negative delta U, negative of the change in potential energy. So delta U, the change in potential energy will be, just put a minus sign here. So this is going to be KQ1 Q2 into 1 by RB minus 1 by RA. Okay, 1 by RB minus 1 by RA. This is delta U. Delta U is always U final minus U initial, UB minus UA. So we calculated this. So when we move from a location A to B, then the potential difference we calculated, this is equal to this value. Okay, so we can look at the signs of this. So if you observe, if I move this charge away, right, then RB is bigger than RA, right? So this becomes negative. So if we try to move the charges away, then delta U turns out to be negative. I think I wrote it here. Yes. So if Q2 moves towards Q1, okay, which means if this is Q1 and Q2, and we bring these charges closer to each other, this is our final, then in this case delta U is positive. Delta U is positive. So if you bring them closer to each other, potential energy increases, and if you make them go away from each other, the potential energy decreases. So that is something to notice. Okay, so now, yeah, so that is the potential difference that we calculated. Before we modify that formula, this is also another interesting question. Here, instead of moving Q2 along the R line, we are moving it along a circle. Okay. Here Q2 is being moved along a circle. Okay, and we have to find the potential difference between A and B. So basically here the thing is, what was the delta U formula? K Q1 Q2 into 1 by RB minus 1 by RA. So here the thing is, when it reaches B, here also the distance is R and the initial distance is also R. So final distance and initial distance are both equal. So in this case, delta U is 0. The potential energy does not change. Potential energy does not change here. Okay. Now, now the thing is, we will set the potential at infinity to be 0. Okay, we are going to talk about a reference point. So in the same formula where we have Q1 over here, we are going to start from infinity. Okay, so infinity is the point A, which is RA distance away, and we are going to finally bring this Q2 charge over here such that it is at a distance R. This is the position B. So from there to there, what is the change in potential energy? It will be K Q1 Q2 into 1 by RB. So RB is equal to R minus 1 by infinity. So something 1 divided by a very large value, this thing tends to 0, right? So, and also we are choosing the infinity as a reference point. Okay, we are choosing the potential energy at infinite separation as 0. Okay, this is mainly just a convention, but you can also think of it like this. When these charges are infinitely far away, there is no interaction between them, right? So the potential energy, you can treat it like 0. So delta U is nothing but UB minus UA, and the starting point is the infinity point. So this we will write it as 0, which means the potential energy at this R location is K Q1 Q2 by R. Okay, this is an important formula. If we have a system of two charges, Q1 and Q2, and they are separated by R distance, then the potential energy of this system is K Q1 Q2 by R. So like if we know this result, we can actually use energy conservation in problems involving this. Okay, because let's say we have two charges itself. This is charge 1, this is charge 2, and charge 1 is, let's say, fixed, and let's say this Q2 is released. Q2 is released at t equal to 0, and initially this was at some R1 distance, So if I release Q2 here, of course, because these are two positive charges, they are going to repel. So Q2 will fly away from Q1, right? So the question is, Q1 is exactly at that old location, but when Q2 reaches some r distance, what is the speed of this charge? Okay, that is the question. It will gain some speed after some time. So in questions like these, we can use energy conservation, because there is no, if I take these two charges as a single system, as my system, there is no net force acting on the system. The net force acting on the system is 0. Actually, that is not that true. Okay, I'll explain why. Because there will be some external force holding this Q1 in place. But the thing is, the only force doing any work, is the electrostatic force on Q2. The Q2 is the charge that is moving, and on Q2 we have the electrostatic force, right? So only force doing any work is the electrostatic force, and work done by electrostatic force, we don't have to do that integration again. We can use the potential energy result. So we can just say the initial total mechanical energy, which is Ui plus Ki, equals final mechanical energy, Uf plus Kf. So initially kinetic energy is 0 because both charges are at rest. Initial potential energy is K Q1 Q2 divided by R1. Final potential energy will be K Q1 Q2 divided by R2. And final kinetic energy, so if Q2 has a mass of m, its kinetic energy will be half m v square. So now you can solve this equation for the value of v. So if you did not know the potential energy result, then you will have to do integration. Okay, then you will have to perform integration to find out the same answer. So v square will be k q1 q2 into 1 by r1 minus r minus 1 by r. Okay, so that will be the answer. So energy conservation can be used in problems involving two charges. And I guess I have a few questions on that. Not this. It's not available here. Anyway, so yeah, that's not okay. Yeah, we have it. So here the distance of the closest approach, okay, of an alpha particle is d when it moves head on towards a nucleus with a velocity v. So alpha particle is basically the helium nucleus, okay. So helium nucleus, it has positive charge of 2e. Its charge is plus 2e, and it has some speed initially with a speed, it is moving with a speed v, and it is headed towards another charge, another nucleus, okay. It is headed towards another nucleus, target nucleus. So here we have a nucleus, and nucleus, of course, it is positively charged, okay. Nucleus has protons, so it is positively charged. Then the question is, if the velocity of the alpha, okay, so closest to distance. So what does that mean? So two positive charges, they repel each other, right? So the force on this alpha particle will be to the left. So this alpha particle will decelerate. The particle is decelerating. So its speed goes down and at some point it will come to rest. At some point over here, it will come to rest. Okay, which means after this point, it won't go to the right. So this is the distance of closest approach. Okay, and they have given that as D. So just use energy conservation, initial potential energy. So they have not given that. Right, so I'm assuming the alpha particle starts from far away. So initial potential energy, we will take it as 0. Initial kinetic energy is half mv square. Finally, kinetic energy is 0. And final potential energy is K Q1 Q2 divided by D. We don't have to substitute anything because this is the comparison question. In the second case, they are saying the velocity is halved. So initial potential energy is 0, but the new velocity is v by 2. Then they are asking what happens to closest distance. So let's say the new closest distance is d dash. So now you just have to take their ratio. Right, so if you do 1 divided by 2, half mv square cancels, and on the left hand side we have 4, and on the right hand side we have d dash divided by d. Right, k q1 q2 also cancels, so d dash comes out to be 4d. So the new closest distance will be 4 times d. Now of course if you reduce the speed, right, then of course it cannot reach this point, it will come to rest much sooner. So if it comes to rest much sooner, closest distance will be greater than d, right? So it cannot be less than d. So these two options are anyway wrong. These two options will be anyway wrong. All right. Now we will take a look at how to write the potential energy when we have 3 charges. So we looked at how to write the potential energy for 2 charges. Now we will write it for 3 charges. Okay, so here the thing is we are also using a slightly different logic to get to the answer. So initially these 3 charges were at infinity. They were very, very far away. So initial potential energy of the system was 0. Okay. They were very, very far away. Now there was an external agent. We have an external agent in picture who's picking up these charges one by one and building the system. So we start with Q1 and we place it over here. Okay. So this is the first step. In this step, the external agent, he brought the charge from infinity to this point. Okay. There is no other charges in the surroundings. So work done will be 0. Okay. There is no force, right? When Q1 is alone, nobody is exerting a force on Q1. So when you move it around, there is no work done. Now we hold Q1 in place and we bring the second charge Q2 and place it at an a distance away. So now our agent, so step 1, I guess it is clear, its work done will be 0. Now in step 2, the agent is bringing the second charge Q2 and placing it at an A distance away from Q1. So now Q2 has entered the picture. Distance between Q1 and Q2 is A. So in this step, okay, and another important thing is this process is performed slowly, performed super slow. Okay. So it's not like we are accelerating the charge Q2 and bringing it here and it has some speed. No. We are bringing it very slowly. So in this process, if you use the work energy theorem, then you can write the work done by the external agent in step 2, okay, which I am writing it as W2, will be equal to change in kinetic energy of the system plus change in potential energy of the system. Okay. So delta K is 0 because process is slow. Okay. So work done in step 2 by the agent is equal to change in potential energy in step 2. Delta U in step 2. So in step 2, we are bringing Q2 from infinity where the potential energy was 0 of the system to this point. Now the potential energy is K Q1 Q2 by A. So W2 we can write it as K Q1 Q2 divided by A. This was the final potential energy minus 0. Okay. So work done by agent in step 1 is 0. In step 2 it is K Q1 Q2 by A. Now we bring the third charge Q3. Now the agent brings the third charge Q3 and Q3 Q1 is C distance away. This is C distance away and this is B distance away. Okay. Now in the third step, what will be the extra potential energy added? Now Q3 will interact with Q1 and Q2 will interact with Q3. That was the extra terms that got added. So in step 3, the work done by the agent will be K Q2 Q3. Write down these two interactions first. K Q2 Q3 divided by B. And then write these two interactions. K Q1 Q3 divided by C. Okay. So what is the total work done by the agent? The total work done by the agent is basically W1 plus W2 plus W3. First he brought Q1, then Q1 and Q2, then all the three charges were arranged one by one. So just add these. So the answer is K Q1 Q2 divided by A plus K Q2 Q3 divided by B and K Q1 Q3 divided by C. This is the work done by the external agent in building the system. Initially these charges were at infinity. Now they are at these three positions and the work done by the agent in building this is given by this formula. This is pretty easy to remember. It's the potential energy contribution due to Q1 and Q2 plus Q2 and Q3 and Q1 and Q3, right? Due to Q1 and Q2 it will be K Q1 Q2 by distance. Here it will be K Q2 Q3 by B and here it will be K Q1 Q3 by C. And then just add them up. That is your work done by agent. Now for this full process, if I say that work done by the agent is W agent. Using work energy theorem, I can write this as change in potential energy. Using work energy theorem, I can say the work done by the agent in the total process. What was the process again? Bringing Q1, Q2 and Q3 from infinitely far away and forming this triangle. The work done by the agent in that process is actually equal to the change in potential energy. So this is an alternate definition for delta U, change in potential energy. Actually, this we can open up a little bit more. Work done by agent is equal to delta U. Delta U finally, I am saying the final potential energy is some U. Initially, it is 0, right? Because they are infinitely far away. So potential energy of any system, potential energy of a system of charges is the work that an external agent has to perform to slowly build the system. To slowly build the system. Okay, so basically the external agent, he built the system of Q1, Q2, Q3, right? And then we learned that the potential energy of any system is the work that the agent has to do to build that system. Now we already calculated the work agent has to do, right? So that we will equate it to the potential energy. So when I say the potential energy of this system, Q1, Q2, Q3, then the potential energy of the system is going to be K Q1, just write these terms individually, K Q1 Q2 by A, then K Q2 Q3 by B, and K Q1 Q3 divided by C. Just write these terms individually. This will be the potential energy in this configuration, and always we are assuming potential energy at infinity as 0. Okay. So that is the logic, but we also got an additional definition for the potential energy using the work energy theorem. It's also the energy that it takes to build a system by an agent. Okay. So that is something, that is an additional definition. All right. Okay. So that definition is also written here. You guys will get the notes after the lecture. In the notes, this will all be mentioned. Okay, so now yeah, let's do this question. CBSE 2025. So a charge of -6 coulomb is placed at the center B of a semicircle, okay, of radius 5 centimeter. an equal and opposite charge of plus 6 microcoulomb is placed at D, which is 10 centimeter from B. Okay. So basically, if this is 5, DC is 5 and BC is also 5, right? Then they're asking a charge of plus 5 microcoulomb is moved from point C to point A. Okay, they are moving another charge which is 5 microcoulomb from C to A along this semicircular path. Okay. Then we have to find the we have to calculate the work done on the charge. Okay, so here we can use this relation we discussed a while ago. The work done by the agent is actually nothing. This is what is asked in the question. What is the work done to move that charge from C to A, right? This is nothing but the change in potential energy of the system. So if the potential energy finally is UA and initially it is UC, delta U is going to be UA minus UC. This will give you the work that the guy did to take the charge from C to A. Okay. So what is UA? UA is the potential energy when this 5 microcoulomb is over here. U final basically. Okay. So in this configuration, what is the potential energy of the system? And UC is the potential energy when 5 microcoulomb is at C. So, so the thing is the interaction of 6 plus 6 and minus 6, that is the same before and after. So that term we don't really have to write it. Okay. Other than that, for UA, there is the interaction between 5 and minus 6 and 5 and plus 6. So the distance between 5 and minus 6 is equal to 5 centimeter. Okay. So it will be K into 5 microcoulomb into minus 6 microcoulomb divided by distance between the two charges, which is 5 centimeter. I'm not doing the calculations, but I'll mention it here. The first thing I'm writing is UA. First, let's write UA. So this is the interaction between 5 and minus 6. Now the interaction between 5 and plus 6. So that will be K into 5 microcoulomb into 6 microcoulomb divided by distance between them. So that is going to be 10 plus 5, 15 centimeter. Okay. Now there is also the interaction between 6 and minus 6. You can write that also. I'll explain why that is not needed. K into 6 microcoulomb into minus 6 microcoulomb divided by distance between 6 and minus 6, that is 10. Okay. Now in the final case, this is actually UA, right? This is the final potential energy of the system. Initially the 5 microcoulomb was over here. Okay. So that, let's call it UC. Now once again write everything. So between plus 6 and plus 5, it is K into 6 into 5, and the distance between them is 5 centimeter. And between 5 and minus 6, it is, so the negative charges you should substitute with their negative sign. Okay. Divided by distance is 5 centimeter. Okay. And finally we have plus 6 and minus 6 once again. So it will be K into 6 microcoulomb into minus 6 microcoulomb divided by 10 centimeter. Okay. Now the reason why I said 6 and minus 6 is not needed is because when you take their subtraction, this cancels out anyway, right? Because initial situation and final situation, both this 6 and minus 6 has not moved. So their contribution will be the same in the initial and final situation. Only the other 4 terms will change. Okay, so now if you need the work done, all you have to do is find whatever this value is and do UA minus UC, U final minus U initial. That will give you the work done by the external agent. Okay, and here when you substitute, you have to substitute K as 9 into 10 raised to 9, and microcoulomb you have to convert it into coulombs, and centimeter you have to convert it into meters. Okay, so that is this question. Any question where work done to do a process is asked, it is simply delta U. Okay, all you have to do is find U final and subtract it with U initial. That will give you the agent work done. It doesn't matter if you move it along this semicircle or some random path like this. Okay, that is the idea of a conservative force. The path does not matter. The only thing that matters is the initial point and the final point. Okay, so that is this question. Yes, this is mainly for boards. Okay, so I have taken boards questions only. But I like the theory part. You can also do it for mains also, but the questions are boards level only. Okay, questions are boards level only. Then so now we are done with electric potential energy, and now we will talk about electric potential. Okay, we will talk about electric potential now. Okay, so electric potential also idea is very similar to potential energy itself. So we will build the logic using potential energy. So in electric potential, when we are talking about it, we fix one charge, let's say over here, we'll call it as Q. And then we have our second charge which we move around. Okay, so this guy we will call it as the test charge. Okay, no particular speciality about this charge, but this is just a charge that we are moving around. Okay, now if we move around, if we move this Q naught charge from some location, let's call this location as RA to this location RB, we discuss the potential difference. When we move along a charge through some path and initial distance is RA and final distance is RB, we calculated the potential and energy difference in this case, right? Potential energy difference in this case was K capital Q into Q naught into 1 by RB minus 1 by RA. This was the potential energy difference. Now, this potential energy difference is directly proportional to the test charge Q naught, right? So, we want the electric potential is defined electric potential due to Q. We use a symbol V for that. Okay, V is, let me write like this. V is the symbol used for electric potential. Okay, and so what was the definition of potential energy? Its definition was, if we are taking Q naught from RA location to RB location, Okay. What is the negative work done by the electric field, right? Electric potential is basically similar only, but for a unit charge. Okay. Electric potential, instead of a Q naught charge, we want the work done to move a 1 coulomb charge around, a unit charge around. So, so this basically electric potential difference is defined as the potential energy difference divided by Q naught. So we want to get rid of this Q naught dependency. Okay. So this will be equal to, if you get rid of the Q naught dependency, it will be KQ into 1 by RB minus 1 by RA. Okay. And similarly, if you consider the initial point as infinity, so delta V is of course VB minus VA. So if I consider, sorry, this will be RB minus RA. So if I consider initial point A as infinity, so this will be 0, 1 by infinity. And I am also considering potential at infinity as 0. So the electric potential due to Q charge, capital Q charge, at some R point away is KQ divided by R. Is KQ divided by R. Okay. So that is electric potential. It's simply potential energy divided by the other charge, the test charge, and that will give me the potential, electric potential of plus Q charge. So if I only have a plus Q charge present in the system, the electric potential at a point P, which is R distance away, now I don't need a charge. Okay, now I don't need a charge. This will be KQ divided by R. Okay, the potential due to plus Q at that point will be KQ divided by R. Now the potential is, as you all know, it's a scalar quantity. Okay, and its SI unit is volt. Okay, and 1 volt we can also represent it as, so using the formula, it's energy divided by charge, right? So 1 joule per coulomb, energy divided by charge. Energy's SI unit is joule, charge SI unit is coulomb. Okay. So that is the idea of the electric potential. And now the thing is, if you take, let's say initial point is R1 and final point is R2 distance away, and this is A point and this is B point. The potential difference is KQ into final potential is KQ by R2. I am writing it like this: KQ by R2 is the final potential minus KQ by R1 is the initial potential. Okay. All right. So this is how we write the potential difference due to a Q charge. All right. So now if you have multiple charges, okay, Q1, Q2 and Q3 and basically any number of charges, and you want to write the net electric potential at some point P, then as it is a scalar quantity, all you have to do is add up their individual contributions, V1 plus V2 plus V3. That will give you the total potential at point P. Okay. For a vector, you will have to do vector sum, but for a scalar, you simply have to add it up. So if Q1 and P, the distance between these two is R1, and Q2 and P, the distance is R2, and between Q3 and so if this distance is R1, and if this distance is R2, and if this distance is R3, then the net potential at point P is V1 plus V2 plus V3, which is KQ1 by R1 plus KQ2 by R2 plus KQ3 by R3. Basically, just add up their individual potentials. Okay. As this is a scalar quantity, there's nothing to think about. You simply have to add them. If it was a vector, then you will have to do vector addition, like for the electric field. So now there is something known as the equipotential surface. Problems of potential of dipole. Okay, potential due to dipole, we'll get to that. Okay, we'll get to that. Okay, so now let's talk about the equipotential surface. So equipotential, this word means same potential. Okay, the word simply means same potential. So whenever equipotential surfaces are asked, what they're asking is, what is that surface where everywhere the potential is the same? The potential has the same value. So for a point charge, it is actually going to be concentric spheres. So if I choose a plus q charge at a distance r, what is the potential? Potential is kq by r, right? It is the same everywhere on this r radius sphere. So if you draw a sphere of radius r, everywhere on the sphere, the distance of plus q from any point on the sphere is actually r itself, right? So what that means is the potential everywhere on the sphere is constant. V on this sphere is constant. It has the same value everywhere. Okay, and the value is kq by r. So this sphere is a equipotential surface by that definition. Okay, let's take a random value. Let's say if V equal to 10 volt. If the potential of this sphere at this R location is 10 volt, then that means everywhere on the sphere the potential is 10 volt. Now, if you choose a different sphere at some R2 distance away, this will be at some different potential, let's say 30 volt. But this will also be an equipotential surface because everywhere the potential will be 30 volt. So if you are talking about a positive charge, it will be these concentric spheres. Okay, the equipotential surfaces are going to be spheres. Any point you take on this sphere, the potential will be the same. Similarly, any point you choose on this inner sphere, the potential will be same. Here, same in this sphere, and in this sphere also it will be same. So for a point charge, the equipotential surface are going to be spheres. Okay, spheres with the same center. Then there is also another fact. The equipotential surface is so this is the main definition. For a point charge, we already covered it. This is also very important. Electric field lines, if you draw it, they will always be perpendicular to an equipotential surface. Okay, so this is the equipotential surface for the plus q charge. Okay, these are going to be spheres, and that is the field line for a plus q charge. And as you can see, they are going to be perpendicular to each other. So if you choose this point, the surface is perpendicular to, the sphere is perpendicular to the field line, right? Here also sphere is perpendicular to field line. So at every point, the field line is perpendicular to the equipotential surface. This is a property of equipotential surfaces, an important one. Okay, electric field will be perpendicular to an equipotential surface all the time. Okay, and then that was for the point charge. Now we can also talk for the uniform electric field. Uniform electric field is basically constant electric field, and when we draw a constant electric field, they are always parallel lines. Okay, parallel lines that are equally spaced, they have equal spacing between them. That is how we draw a uniform electric field. Okay, and what will be the equipotential surface in this case? It's going to be these planes. Okay, from this picture it won't be clear, but these are going to be the equipotential surfaces, parallel planes. So this is the electric field vector, and these yellow lines are the equipotential surfaces. Just draw perpendicular surfaces to the electric field. Okay, so as you can see, this surface is perpendicular to the field. So you get the equipotential surfaces. So they are actually parallel planes. Parallel planes. From the side view, they will look something like this. Okay, they are going to be these parallel planes. Here, let's say the potential is V1. Here the potential will be V2 everywhere on this plane. Here the potential everywhere on the plane will be V3, and so on. So these are the equipotential planes if we have a uniform field. Okay. Now this is an important formula for boards. They consistently ask this question all the time. What is the relation between the potential difference and the electric field at a point? Okay, this question is consistently asked. So not this diagram. So here the thing is, let's say I have two equipotential surfaces like this. Okay, that are very close to each other, and this perpendicular distance, I'll draw it a little bit further away so that it is clear. So the perpendicular distance between, so these two are equipotential surfaces. Okay, so I'm saying this surface has potential V and this surface has potential V plus dV. Okay, also, what was the formula for delta U in terms of the electric field? This was negative of the work done by the electric field to go from A to B, right? So this I can also write it as minus integration okay, so this I'll have to cover it a little bit. So in this particular page, when we derived the potential difference, right? Here we were moving a Q naught charge while keeping Q fixed. Okay, so here if I want to write the work done by the electric field, there is also, I can use the integration formula. So what is the electric force on Q naught? Let's say the field, electric field due to Q is E. Okay, the electric field due to Q, capital Q, I am saying it is equal to E. So when Q naught is over here, the electric field will be in this direction. So if I want to calculate the work done from this point to this point, this is slightly complicated, but the formula is more important. If I want to calculate the work done from A to B of the electric field, it will be the electric force, which is Q naught into E vector. This is the electric force on the charge Q naught dot displacement. Okay, you can also use dl vector for displacement, and you have to do this from A to B. That will give you the work done. Now this we can also write it as minus delta U from the first formula we discussed. So from here you can also see delta U is minus, that Q naught is a constant, so take it outside, integration of E dot dl or E dot ds from A to B. This is delta U, which is UB minus UA. Now potential difference is delta U divided by Q naught. Potential difference will then be delta U by Q naught, which is simply negative integration of E dot ds from the point A to B. This will give you the potential difference. So in this page, I will just write it once again. Delta V is going to be minus integration of E dot dl from A to B. So if you want dV, then it will be minus E dot dl. Minus E dot dl. So here, from here we are going to notice an important fact. If E dot dl is positive, okay, what does E dot dl positive mean? I mean that means E and dl, that means dl and E have an acute angle between them. Theta is acute. Okay. But if E and dl are parallel to each other, then also E dot dl will be positive, which means if you're walking in the direction of the electric field, then dV will be negative. If E is parallel to dl, assume, this means theta is 0 degree, okay. So dV will be minus E into dl. Okay, this is negative. This means potential decreases. V decreases. So when we are walking in the direction of the electric field, let me just take an example where the electric field is in this direction. Electric field is perpendicular to the equipotential surface, right? Like this. So if I am walking in the direction of the electric field, okay, then E dot dl is positive, right? Which means dV must be negative. dV must be negative. So potential must decrease. So, so if I say the potential here is V plus dV, the potential here will be V. So that is the important point. In the direction of the electric field, the potential will decrease. Potential is decreasing. Okay, so I'm not going into much detail because time is about to be over. So now what we'll do is, in the same relation, right, we are just going to use this one relation itself. What is the electric field from here? The electric field will be minus dV by dl. minus dV by dl. But here there is a slight catch. dl, this dl over here is perpendicular to the surface, to the equipotential surface. Okay. So that is the formula. Now there is also another important formula. This is not given in NCRT, but they have asked it in board exams, which is the partial derivative formula. Okay, so now what we are going to do is, I know the potential here is V and the potential here is V plus dV, right? So actually just take the potential here as V plus delta V. Okay, let's first work with delta, and here it is V. Okay, because in the direction of the field, potential must decrease. Now let's say this is the x direction and this is the y direction. So we are walking in the x direction first. Okay, we are walking from path A to point C in this direction, and in this direction the field is Ex. What is Ex? X direction electric field. X direction electric field. Okay, so now use that formula. Delta V or dV, you can write it as minus Ex into delta x. Ex into delta x. You can write it like this. And what is delta V? It is potential of the C point minus potential of A point, right? So actually, yeah, just keep it like this only. Okay, potential of C point minus potential of A point, that will be, so this is an equipotential surface, right? So potential of D, B, C, all of it is V plus delta V, and potential of A is V. So delta V is going to be potential of this minus potential of this, which is delta V itself. So from here what we are getting is Ex is equal to minus delta V by delta x. Okay. Now for very small delta x's, for very small delta x, we are going to treat delta x like dx, and we get the x direction field as minus dv by dx. But there is a catch here. This is not simply minus dv by dx. It is minus partial derivative of v with respect to x. Okay. And similarly, if you do it for the path including delta y, you will get Ey as minus partial derivative of v with respect to y. And here we don't have z, but in case z was also there, Ez will be minus partial derivative of v with respect to z. So in total, if you have the potential, okay, if potential function is given to you and you want to find the electric field, then you will have to use these relations. Now, what does partial derivative mean? I'll explain that using a question. Okay, we'll do a question and understand that. So this is a CBSE question, and here potential is given as 10 minus 50x, and the question is find the electric field. Okay, find the electric field. So here Ex, if you want, it will be minus dou V by dou x. But here the thing is, the potential is only dependent on x. There is only x in this equation, no y and z, which means electric field will only be in the x direction. Okay, so you can simply write this as dV by dx itself and just differentiate this. So what is the differentiation of minus 50x? It will be minus 50, but there is already a minus outside, right? So this is going to be 50, and SI unit of electric field, we will write it as Newton per Coulomb. Okay, and it came out to be positive, so it is along plus x direction. Okay, so if only x is there in the equation or only y is there in the equation, then electric field will only be in one direction. Okay, so here potential is along x, so electric field will also be along plus x. So the answer is, wait a second, 50 Newton per Coulomb along plus x. Okay, you have to be careful about this minus sign, do not forget about that. But there is another question here, not this one. Here if you notice, the potential, it depends on x and y both. Okay, which means there will be Ex and Ey. There will be a field in x direction and y direction. Okay, so we will have to separately find it. So now focus on this. The electric field along the x direction will be minus partially differentiating v with respect to x. Now what does this mean? This means differentiate x but keep everybody else a constant. So if there is y in the question, you have to treat it like a constant. Okay, and only differentiate x. So this dou v by dou x, this means treat y comma z like a constant and differentiate x normally. Okay, differentiate x normally. So here 1x square's derivative is 2x. Okay, so this is the electric field in the x direction. Similarly, electric field in the y direction will be put a negative sign and partially differentiate this 2y square. So that will be minus 4y, right? This will be minus 4y, which is actually plus 4y. This is the y direction electric field. So if you want the total electric field, it will be minus 2x, this is the x direction component, and plus 4y, this is the y direction component. Now they have given a point 2, 1, so you have to put it here. So electric field at 2, 1 point, instead of x put 2, which is minus 4i, and instead of y put 1, which is plus 4j. Okay, so the question is not what is the electric field, but what angle does electric field make with the positive x-axis. So there are some vectors here. So electric field, we found it out as minus 4i plus 4j. So if this is the x-axis and this is the y-axis, this is the origin, plot this vector. So the vector has a minus 4i component. Minus 4i means 4 units to the minus x direction and 4 units along the j direction, plus j direction. So 4 along the left, 4 and 4 along the J. So this is your actual electric field vector. Minus 4I plus 4J. So that will be your actual electric field vector. What the question asked is, what is the angle electric field makes with positive x-axis? So this angle is what they asked. This angle is simply 45 degree, right? This angle will be 45 degree because this is a 4-4 triangle, right? So tan theta, if you do, it will be 4 divided by 4, which is 1. So tan theta 1 means theta 45. So this angle will be 180 minus 45, which is 135 degree. Okay, and this is what the question asked. 135 degree will be the answer. Okay, so if potential is given to you and it has x and y both, then you have to find Ex and Ey. Okay, so that is something to keep in mind. All right. Okay, Anil, you have a question. A is minus 10 volt, B is plus 20 volt. Okay, so if A is okay, so if point A, I'll just ignore the numerical value. If the point A has potential VA and point B has potential VB, okay, then the potential difference, I guess you want to find the work done by the agent, I guess. Yeah, so when you're saying find work done, we mean work done by agent, okay. So work done by agent is always delta U, which is final potential energy minus initial potential energy. Now delta U we discussed a while back. You can write it as Q into delta V, right? Delta V was delta U divided by Q. So Q delta U, you can write it as Q into delta V. Okay. So if you are taking a plus Q particle from A to B and potential of A and potential of B is given, then the work that we have to do is simply Q delta V, okay, which is Q into VB minus VA. But in your question, it's an electron. So I'll just answer it for a negative particle, okay. So if the charge is actually minus Q, then instead of Q, you will have to put minus Q, okay. In that case, it will be minus Q delta V if it's a negative charge, which is minus Q into VB minus VA. This will give you the work in the case of the electron. So basically all you have to do is here substitute minus 1.6 into 10 raised to minus 19 and then substitute VB and VA, okay, whatever that value may be. This will give you the work done by the agent, okay. Okay, is that fine? Okay, so electron volt, okay, if they are asking in electron volt, then you don't substitute this value, because if you substitute E, then you will get the answer in joules, okay. Then you get the answer in joules. But if electron volt is asked, just don't substitute this, okay. It will simply be VB minus VA into E. This much electron volts. Okay. All right, guys. So I guess the time is over. So we can end the lecture here. Okay, good night, guys. Take care. Whatever is left in this lecture, we will take it in the next one. Okay. All right.